Hello everyone, my name is Sakib Chowdhury. I am a master's student at the University of Waterloo in Waterloo, Ontario, Canada, and today I am here to talk to you about our work on a scalable recoverable skip list for persistent memory. Starting off with some background information, a skip list is a data structure that implements a key value store, which is a useful collection type for database indexes. Skip lists have logarithmic time complexity on average for searches, achieved through its probabilistically built structure. When inserting, a new node is given a random height and linked in at all levels, with searches traversing sparser levels first. Next, persistent memory is a form of non-volatile storage that is byte addressable by the CPU at low latency, combining the benefits of both RAM and secondary storage. Changes to a PMEM data structure can survive a power failure without being written to disk, as long as they've been flushed out of CPU caches and into the persistent domain. Now, if the CPU is halfway through performing an operation when a crash happens, upon recovery the data structure may be in an inconsistent state. As a result, recoverable data structures have to be made to return to a consistent state after recovery. Building new data structures to do this is difficult, so one way to go about it is to convert existing non-recoverable algorithms. Recipe is a conversion technique published in 2019 by Lee and others that dictates some ways to do this. An update that consists of just a single atomic store, like swapping out a single pointer in a linked list, is easy to make recoverable simply by inserting a flush after the operation. Now, whether a crash happens before or after a flush, both cases result in a consistent data structure. For more complex modifications involving multiple swaps, Recipe offers two solutions. In the case where an operation in progress can be helped to complete by another thread, as in wait-free algorithms, the same helping mechanism can be used to finish the operation. If there is no helping mechanism but updates are blocking, a thread that observes an inconsistency can check to see if the inconsistent node is locked. If it is locked, then there must be another thread that locked it and has responsibility for its consistency. Otherwise, the thread that would be working on it must have died during a crash, in which case this thread knows it should help. But what if there is no helping mechanism and no locks to check? One solution is to keep track of when a node was created. If we give each period of operation between two crashes an epoch number, then a node modified during the current epoch can be updated to indicate the last time it had a thread responsible for it. This way, upon finding an inconsistent node, a thread can check the epoch of the node to identify if it needs to be recovered, or if the thread can ignore it and keep going. If it needs to be recovered, the thread first updates its epoch number as shown in the pseudocode to claim it, preventing multiple threads from trying to recover the same node at once. As a visual example, in this skip list, a thread is busy inserting the yellow node. An observing thread notices an inconsistency due to the update in progress, but given the epoch is current, it knows that another thread is busy inserting it. Now, if a crash occurs before the first thread changes the pointer, the yellow node remains incomplete and its epoch number is outdated. Now, an observing thread that notices the inconsistency can see from the epoch number that this node will remain incomplete until somebody does something about it. That brings us to the untitled persistent skip list, or UP-skip list, retroactively named after the Untitled Goose Game from 2019. It is a recoverable adaptation of Herlihy and Schavitz's lock-free skip list algorithm, which lacks helping mechanisms and has non-blocking writes. Some performance improvements can be made to this extension and to the skip list. Checking the epoch number first instead of looking for inconsistencies can tell us whether inconsistencies have to be looked for at all, saving a lot of time. The skip list algorithm itself can also be modified to hold multiple keys per node within an array. This modification can easily be made recoverable by adding additional inconsistency checks and repair mechanisms performed when a node is found to be outdated. Finally, performance can be further improved by throwing more cores at the data structure using a NUMA machine with the data striped across storage local to each NUMA node. For performance evaluation, tests were run on a 4-socket Intel Xeon machine with 80 cores and 160 threads with hyperthreading, with 3 TB of persistent memory. Comparison was done against BZ-tree, or as the Americans call it, BZ-tree, which is a B-tree with non-blocking, non-repairing writes implemented with the persistent multi-word compare and swap primitive, or PMWCAS. The tests were run using standard Yahoo Cloud Serving benchmark workloads, representing common database access patterns, and prior to each test the structures were preloaded with 100 million key-value pairs. Looking at the result, it can be seen that UP-skip list outperforms BZ-tree whenever there is a relatively large amount of updates, as seen in the update-heavy and read-mostly workloads, which are 50% and 5% updates respectively. On the other hand, when only reading or reading recently written data, BZ-tree outperforms UP-skip list. This is a result replicating that of Lersch and others from their index data structure evaluation paper, which also took a look at BZ-tree. Popping the hood, it turns out that BZ-tree's update performance is limited by its use of PMWCAS, which introduces bottlenecks that choke the updates when too many are occurring at once. Meanwhile, its read performance is bolstered through its sorting of keys stored in a node after a node split, allowing a binary search to be used on the sorted portion, while upskiplist is stuck doing a linear search inside a node in all cases. This optimization is not inherent to BZ-tree and can be implemented in upskiplist to further improve its performance, hopefully until it's competitive in all workloads. In conclusion, Recipe can be extended to work on data structures with non-blocking, non-repairing writes, using the epoch tracking method presented in this paper. Using this extension, upskiplist, a recoverable skiplist, compares favorably to BZ-tree, a competing data structure. If you have any questions, please feel free to send me an email at sakib.chowdhury@uwaterloo.ca. Thank you for your time, and I hope you enjoyed this presentation.